Hello students, in this lecture we will be discussing about the Muller-Breslau principle, and we will also be discussing about its application in influence line diagram, how it is useful in constructing influence line diagram for both determinate as well as indeterminate fields. Mainly we will be concerned about the construction of constructing an influence line diagram for indeterminate fields. Myself, Shubhanshu Jaiswal, Assistant Professor at University, Lucknow. So, first of all, we need to know uh, basically where the name came from. The name Muller-Breslau came from the scientist called as Muller-Breslau. His real name was Heinrich Franz Bernhard Muller, and basically he was from the city of Breslau. So, due to which his name was also known as Muller-Breslau, and this is how he got famous by the name of Muller-Breslau. Basically, it means Muller was his name, and Breslau was the city where he belongs. Uh, he has provided a significant contribution to the theory of beams and frames in a structural analysis, and he was the one who gave the Muller-Breslau principle, depend based on the influence line diagram. So let us first understand what this Muller-Breslau principle says. The statement of a Muller-Breslau principle, what it says. Muller-Breslau principle states that if we give a statement of Muller-Breslau principle, it is like if an internal stress component or a reaction is considered to act for some small distance, and they by to deflect or displace the structure, the curve of the deflected structure will be to some extent the influence line of the stress or the reaction component. Basically, it simply says that the deflection shape of a structure under load somehow represents the influence line diagram for that particular reaction component or stress function. So if we say for a reaction, the variation of a reaction from one point to other, then its deflected shape under that load will represent the ILD for the same beam, and this is what the Muller-Breslau principle is. The application for this can goes like if we get the deflection shape of any beam, and using that we can uh, draw the ILD of the beam. This we'll discuss in more detail by using an example in the upcoming slide. The other ways of stating this principle is the ordinate of influence line diagram for a reaction is given by the ordinate of elastic curve if a unit deflection is applied in the direction of a reaction. But the ordinate of an elastic curve simply says a deflected curve. Ordinate of a deflected curve. Remember, when a unit deflection is unit deflection or unit force is applied on a beam and is allowed to move from one point to another, then the deflected shape will represent the influence line diagram for the same function. This principle is valid for the functions, various stress functions like reaction, shear force, bending moment, forces, etc. So these are the components which we have already studied in the detail cases when we studied influence line diagrams for different cases of beams as well as frames. Now, let us see by using this example. In this case, this is a beam. This is a simply supported beam, which has a support at A, another support at B. At support a reaction Ra is acting upward because of this support. So this reaction Ra will create a force in the upward direction and will allows this support to move in the upward direction, and a very small deflection, say delta, occurs in the upward direction, and the shape, and this is like this. So if we see the deflected shape of this beam, then it can be easily represented by a dotted line. This part has shown a deflection of delta, and this part has shown a negligible deflection, say 0. So the variation of deflection from this part to this end will be represented as a dotted line. And as we have studied, for a simply supported beam, if we see the ILD for support reaction, then it is like this. So this is how we can easily uh, relate an ILD from the deflection or the elastic curve of a beam. So if we get this elastic curve or deflection curve of a beam, we will be able to draw the ILD as well. So this is the basic principle of this. This is the application of this principle called Muller-Breslau principle. So same usefulness of the Muller-Breslau principle is the application of it. Muller-Breslau principle is applicable to all structure, determinate or indeterminate. As I told you, Muller-Breslau principle is used to calculate the influence line ordinates for both in determinate or indeterminate structure. But the condition is that the structure should be within an elastic limit. That simply means it should follow Hooke's law, because if a structure do not follow a Hooke's law, if it do not follow the Hooke's law, then we cannot simply apply the law of superposition. So in order to apply the law of superposition, the structure should be within the elastic limit and it should follow the Hooke's law. The other thing about this principle is it gives an excellent experimental approach to determine the influence line for indeterminate structure. Next example that we will be considering will also be for indeterminate structure, in which we'll try to calculate the ILD using influence Muller-Breslau principle. So here is example. There is example of a continuous beam, in which in this example we need to compute the ordinates of influence line for Ra. We need to draw simply the influence line for Ra and its ordinates from point A to point C. Say, let us first read the question first. Lines of reaction Ra of a beam shown in figure at an interval of 1 meter, and draw the influence line diagram. The moment of inertia is constant throughout. So this beam is a continuous beam having a support at end A, center B, and C. Uh, the whole span is of 11 meters, and we need to calculate the ordinates of ILD at 1 meter distance. So first ordinate will be at 1 meter from A, other will be 2, third will be 3, fourth will be 4, and so on till C. So these are the points where we need to calculate the ordinates of influence line diagram. If we simply remove this part, uh, we can simply say the bending moment diagram will be like this. Uh, will be like this, because it is if we apply a unit load over here, because we are concerned to calculate uh, the ILD for Ra, so we'll simply apply a unit load of 1 kilonewton acting upward on point A. Due to this 1 kilonewton load, the reaction on RB and RC can be calculated to be 2.2 kilonewton and 1.2 kilonewton respectively. Now, due to this loads, uh, 1 kilonewton, we can calculate moment at B to be 6 kilonewton. So the bending moment diagram will be like this. Now, this is a beam. This is the ordinate selected that we can see it due to unit load in a beam. This is how the ordinates looks like. This is a bending moment diagram. This is a M upon EI diagram. Remember, we are going to use conjugate beam method here also. This is a M upon EI diagram. Simply 1, 2, 3, 4, 5, 6 are the moments, and bending, and this is divided by EI, so it is called M upon EI diagram. This is a case where we have applied a resisting moment over here. So we'll be calculating MA dash also, and this is the curve we'll discuss later. This is a basically ILD for this beam for reaction, and we'll discuss it later. Now let us see the calculation, how we have calculated all these moments. Let us see. Now the restraints in the direction RA is removed, and a unit load in the direction of RA is applied. According to Muller-Breslau principle, the deflected shape of the beam in the influence line diagram of RA, the bending moment diagram of the release beam is shown in figure 5.6c. This is the moment diagram. To find a deflection in the release structure, consider the conjugate beam. This is what I just told you. This is a M upon AI diagram. This is a conjugate beam diagram. Now, simply we know in a conjugate beam here we are taking the moment about B to be 0. So here is the end B. So we are taking the moment about B 0 because we know if we draw a conjugate beam, this is a real beam and this is a conjugate beam. So for a real beam, when we draw a conjugate beam, then for intermediate support, their supports becomes a internal hinge, and we know that at hinge the moment is 0. So what we can do, we can simply equate the moment about B to be 0, and that's we have done over here. That's what we have done over here. Sigma MB is equals to 0. So we will be taking moment about B. Moment about B will be what? In this case, that is RA into 6 and MA. That is RA. They have taken it off from here. Okay, no problem. Similarly, RC dash into 5. This is RC dash into 5 is equals to 1 upon 2. This is the area of a triangle, half into 6 upon EI. This is a triangle. This is a triangular load that will act. So this is the as per conjugate beam method, the loading diagram becomes the the M upon EI diagram for the real beam becomes the loading diagram for the conjugate beam. So if we are calculating the moment at this point B, then the moment will be due to this reaction RC and this triangular load uh, that is acting downward. So the load of this triangular, uh, the magnitude of this triangular load will be half into basis 5 into height is 6 upon EI. This is half into base into height into 5 by 3 the distance. So this is how we can calculate RC dash. Now we can easily say that sigma V is equals to 0. That is shear force. Sigma V is basically the sum of all the vertical reactions is equals to 0. It is one of the equilibrium equation. We can easily say RA dash plus RC dash is equals to the load of the whole triangle. This is the load of the whole triangle. RA dash plus RC dash is equals to the load of this whole triangle. And the load of this whole triangle is half into base is 11 meters into height is 6 upon EI. See, half 11 into 6 upon EI, that is 33 upon EI. So this is how we can simply we know the value of RC. We'll put the value of RC over here and we'll get the value of RA dash. So RA dash and RC dash are now known to us. Next, what we can do, we can simply take moment about A and equate it to 0. So this is the third equilibrium equation. We'll say MA dash plus this is reaction due to RA, this is reaction due to RC, and this is the distance. It will be equals to 0. this equation will give the value of ma dash, and that is what we are concerned with. Ma dash, now ma dash is this moment ma dash that is acting over here. So this moment is being calculated now. It is 132 upon ei. Now we know that ma is equals to minus 132 upon ei. This is the uh, uh, sagging moment, and it can be termed as negative because it is making the beam sagging. So it will be minus 132 upon ei. So m1, basically m1 is the moment at the ordinate 1. M2 is the moment at ordinate 2. Here are the ordinates. This is 1, this is 2, this is 3, this is 4. M1 is the moment here, M2 is the moment here, M3 is the moment here, and so on till M9. So M1 is basically what? It is simply 132 upon EI plus 28 upon EI multiplied by 1. This is 1, this is due to the unit load. And this is how we can calculate simply by taking the moment. M1 to be 104.33 upon EI, M2 is equals to 77.33 upon EI, M3 is equals to 52.5 upon EI, M4 is equals to 30.67 upon EI, M5 is equals to 132. This is M5 is equals to this, and MB, we know that MB will be equals to 0 because moment at this part, this is a hinge, will be equals to 0. Now for the portion BC is this portion, MC is equals to 0. So M9 will be calculated to be 4.8 upon EI. This is M8 8.4 upon EI. This is M7 9.6 upon EI. This is M6 7.2 upon EI. So these all are the moments. Now what we have to do, this was a very simple part. We have already studied in the conjugate beam method. Now the twist comes, that how we can calculate the influence line diagram ordinates using these moments. So this is the basic thing that we need to remember, that influence line diagram ordinate at A will be equals to a deflection at A in release beam. This is what the application of a Muller-Breslau principle. By using Muller-Breslau principle, we can simply say that influence line diagram ordinate at A will be equals to the deflection at A in the release beam. And we know that for a conjugate beam method, the deflection in the real beam gives the moment in the conjugate beam. So we can say that deflection at A will be equals to moment in the conjugate beam at A. And we have already calculated the moment in the conjugate beam at A is equals to 132 upon EI. We have calculated here 132 upon EI. So we can simply write down as 132 upon EI, and this will represent the deflection at A. This will represent the deflection at A, and it will also represent the influence line diagram ordinate at A. But remember, this value 132 upon EI is due to the whole load, but here a unit load is applied. So in order to get a unit load, you need to divide 132 upon EI by 132 upon EI, and this will give the value of 1. Similarly, here you need to divide the value of moment at 2. This is 77.33 upon EI divided by 132 upon EI, and that will give the value 0.79. Similarly, for M3, the value of moment is 52.5 upon EI, and we'll divide it by 132 upon EI, and this will give the value of 0.586. Similarly, 0.398. Similarly, 0.232. And at this point, the moment will be 0. We can easily see this is a hinge. So at hinge, we know that moment is 0. So this can also be said as a point of contraflexion. And here the moment, the deflected shape or the ILD goes like this, and here again it becomes 0. So this curve is the ILD for reaction RA in this case, and it can also be said as it is a deflected shape for RA. So this is how we using Muller-Breslau principle, we can easily calculate the ILD ordinates for any of the beam, and this is the application of a Muller-Breslau principle also. So in every case, we can simply use this principle to calculate the influence line diagram for a beam. So this is how we can, this principle makes the things easier for us in the structural analysis. Thank you, class.